Section: Introduction. In this section, we discuss recent advancements in reasoning-focused language models, like OpenAI O1 and DeepSeek R1, which have transformed artificial intelligence by enhancing test time computation. This test time scaling allows for extended chain-of-thought reasoning, improving performance on complex tasks such as math problem-solving and code generation. By continuously using computational resources during reasoning, through exploration, verification, and backtracking, models can achieve better results, although this results in longer reasoning traces. Central to these advancements is reinforcement learning, RL, which plays a crucial role in developing advanced reasoning skills. By focusing on verifiable rewards instead of learned reward models, RL systems can avoid issues like reward hacking and align more closely with correct reasoning. However, a key question remains: does RL truly unlock new reasoning abilities in a base model, or does it just enhance the efficiency of existing solutions? Some recent studies suggest the latter, arguing that RL-trained models do not gain new reasoning skills beyond what their base models already possess. We believe these conclusions may arise from methodological issues rather than limitations of RL itself. We identify two main constraints in current research. 1. An excessive focus on specialized areas like mathematics, where models are often overtrained, limiting exploration. And 2. Ending RL training too early, typically after only a few hundred steps, which prevents models from fully developing new reasoning skills. To address these limitations, we introduce ProRL, a method that allows for longer RL training periods, enabling deeper exploration of reasoning strategies. ProRL supports over 2,000 training steps and uses diverse tasks, including math, coding, STEM problems, logical puzzles, and instruction following, which we believe are essential for generalization. Using ProRL, we created Nemotron Research Reasoning Qwen 1.5b, a leading 1.5 billion parameter reasoning model that significantly outperforms its base model, DeepSeek R1 to 1.5b, and matches or exceeds the performance of DeepSeek R1 to 7b across various benchmarks. Notably, we see average improvements of 14.7% in math, 13.9% in coding, 54.8% in logic puzzles, 25.1% in STEM reasoning, and 18.1% in instruction following tasks compared to DeepSeek R1 to 1.5b. Importantly, ProRL shows continued performance gains even after 2,000 training steps, indicating that RL training benefits from increased computational resources. Moreover, Nemotron Research Reasoning Qwen 1.5b reveals that RL can uncover genuinely new solution paths not present in base models when given enough training time and applied to new reasoning tasks. Our analysis shows that our model generates novel insights and excels at increasingly challenging tasks, indicating a real expansion of reasoning capabilities beyond its initial training. We find instances where the base model fails to produce correct solutions, while our RL-trained model achieves perfect success rates. Interestingly, we observe that the improvement from RL on each task correlates with the base model's initial performance, suggesting that RL is most effective in areas where the base model struggles. We also measure the novelty of the model's reasoning paths using the Creativity Index, which assesses overlap with the pre-training data. Our findings indicate that extended RL training leads to more novel reasoning patterns. Overall, our results have significant implications for the AI community, showing that RL can enhance model capabilities without needing additional training data. Through ongoing exploration, models can develop new knowledge and reasoning strategies that may surpass human insights. This work reinforces the potential of reinforcement learning as a means to create more capable and adaptable AI systems, challenging previous beliefs about the limitations of these methods. Section Summary. In this section, we discuss the advancements in reasoning-focused language models through prolonged reinforcement learning, ProRL, which allows for extended training and deeper exploration of reasoning strategies. Our findings indicate that ProRL not only enhances model performance across various tasks but also enables the discovery of new reasoning pathways, challenging previous assumptions about the limitations of reinforcement learning in AI. Section: Background: Group Relative Policy Optimization. In this section, we adopt Group Relative Policy Optimization, GRPO, as our main reinforcement learning (RL) algorithm. Unlike Proximal Policy Optimization (PPO), GRPO does not use a value model. Instead, it relies on baseline estimates based on group scores. The goal of GRPO is to maximize a specific objective, where we sample responses from the current policy and calculate the probability ratio between the current and old policies before updating. We also address a challenge known as entropy collapse, which occurs when the model's output distribution becomes too focused early in training, leading to reduced exploration. This is particularly problematic for GRPO, as it relies on diverse outputs to accurately estimate advantages. Without enough exploration, our policy updates can become biased, causing training to stagnate. While increasing the sampling temperature during rollouts can help, we find it only postpones entropy collapse rather than preventing it. Nonetheless, we still use a higher rollout temperature to encourage initial exploration. To combat entropy collapse, we incorporate elements from the decoupled clip and dynamic sampling policy optimization (DAPO) algorithm. DAPO introduces decoupled clipping, allowing us to set separate upper and lower bounds in the PPO objective. By increasing the upper bound, we can uplift the probabilities of less likely outputs, promoting broader exploration and helping to maintain entropy. DAPO also filters out prompts where the model consistently succeeds or fails, focusing on examples of intermediate difficulty to ensure a diverse learning signal. We find that while DAPO and temperature adjustments help slow entropy collapse, adding a KL divergence penalty provides a more robust solution. This penalty helps maintain entropy and prevents the online policy from straying too far from a stable reference policy, which stabilizes learning and reduces overfitting. Although some recent studies suggest removing the KL penalty, we believe it remains beneficial, especially since we start from a well-initialized checkpoint capable of generating coherent outputs. To address the issue of the KL term dominating the loss as training progresses, we implement a reference policy reset. This involves periodically resetting the reference policy to a recent version of the online policy and reinitializing the optimizer states. This strategy allows us to continue improving while still benefiting from KL regularization, helping to avoid premature convergence and encouraging extended training. We introduce Nemotron Research Reasoning Quen 1.5b, a generalist model trained through reinforcement learning on a diverse dataset of 136,000 problems across various domains, including math, code, STEM, logic puzzles, and instruction following. By utilizing stable reward computation, enhanced GRPO, and prolonged training, our model demonstrates strong generalization across these areas, outperforming previous models in multiple tasks. Our training dataset is carefully constructed to include a wide range of examples across 5 task domains, ensuring robust reinforcement learning. Each task is paired with a clear reward signal, facilitating reliable feedback during training. This comprehensive coverage promotes generalization beyond specific domains and allows for meaningful comparisons of RL algorithms across different reward structures. Section Summary. In this section, we adopt Group Relative Policy Optimization, GRPO, as our core reinforcement learning algorithm, addressing challenges like entropy collapse through techniques such as decoupled clipping and KL regularization. We introduce Nemotron Research Reasoning Quen 1.5b, a generalist model trained on a diverse dataset of 136K problems, which demonstrates significant performance improvements across various reasoning tasks compared to previous models. Section: Training Setup. In this section, we describe our training setup and evaluation process. We utilize VRL for reinforcement learning training and implement enhancements from GRPO as suggested by DAPO. This includes separating clipping hyperparameters with lower and upper limits of 0.2 and 0.4, respectively, and using dynamic sampling to filter out prompts that are either too easy or too difficult. For each prompt, we sample 16 responses while keeping the context window to 8,096 tokens and set a high sampling temperature of 1.2. Our batch size is 256, with a mini batch size of 64, allowing for 4 gradient updates per rollout step. We employ the Atom W optimizer with a constant learning rate of 2 millionths. Our training occurs on 4 NVIDIA H100 nodes, totaling around 16,000 GPU hours. To support effective long-term reinforcement learning, we track our training progress using a blended validation set from our evaluation benchmark. If we notice that validation performance plateaus or declines, we reset the reference model and optimizer to restore stability and encourage more policy variation from the base model. During most of the training, we limit response length to 8,000 tokens for clarity and stability. In the final phase, we expand the context window to 16,000 tokens, which allows the model to adapt quickly and show improvements. We provide further details in the appendix, and we illustrate key training dynamics in a figure that shows statistics over the course of our extended reinforcement learning. The enhancements from DAPO, along with the inclusion of KL divergence loss, helped prevent entropy collapse in our model. We found a positive link between average response length and validation scores, but this was not always decisive, as there were training phases where performance improved without longer responses. Validation performance, measured by both pass at 1 and pass at 1.6, consistently improved with increased training computation. For evaluation, we assess our models across various tasks, including math, coding, reasoning, and instruction following. In math, we follow benchmarks like Deep Scale R and Simple RL, evaluating on datasets from 2022 and 2023, Math, Minerva Math, and Olympiad Bench. For coding, we use the validation set from Prime, which includes apps, code contests, code forces, and Taco, along with Human Evil Plus and Live Code Bench. We also reserve 100 samples from each reasoning gym task for logic puzzles and use curated subsets from GPQA Diamond and IF Eval for STEM reasoning and instruction following. We employ VLLM as our inference backend, with a sampling temperature of 0.6, nucleus sampling at 0.95, and a maximum response length of 32,000 tokens. For math, coding, and STEM reasoning tasks, we estimate pass at 1 from 16 samples for each benchmark prompt based on binary rewards. For logical puzzles and instruction following, we calculate average continuous reward scores from our rule-based verifiers. We report benchmark results for open-source models using our evaluation settings. In our evaluation results, we compare our final model, Nemotron Research Reasoning Quen 1.5b, with DeepSeek R1 Distill Quen 1.5b across multiple domains. In math, our model shows an average improvement of 15.7% over the base model. In coding, we achieve a 14.4% increase in pass at 1 accuracy. Our model also excels in STEM reasoning and instruction following, with improvements of 25.9% on GPQA Diamond and 22.0% on IF Eval. We see significant gains in logic puzzles, improving rewards by 54.8%, even outperforming a larger model, DeepSeek R1 Distill Quen 7b, in several areas. We also present results on out-of-distribution tasks in Reasoning Gym, where our model demonstrates strong generalization capabilities, indicating the effectiveness of our training approach. Finally, we compare our model with 2 domain-specialized baselines, DEEPSCALER 1.5b for math and DEEPCODER 1.5b for coding. Our ProRL trained model achieves superior pass at 1 scores in both math and coding benchmarks, while allowing for deeper exploration within limited response lengths, avoiding the pitfalls of verbose reasoning seen in prior works. Section Summary. In this section, we describe our training setup using ProRL for reinforcement learning, incorporating enhancements from DAPO, such as decoupling clipping hyperparameters and dynamic sampling, while employing a high sampling temperature and specific batch sizes. We also detail our evaluation process across various tasks, demonstrating that our model significantly outperforms baseline models in math, coding, and reasoning tasks, while showing strong generalization to out-of-distribution challenges. Section: Analysis. Does ProRL elicit new reasoning patterns? In this section, we evaluate whether extended ProRL training improves reasoning abilities beyond what the base model offers. We increase the number of inference samples to 256 and reassess performance. Due to computational constraints, we randomly select 18 tasks from the reasoning gym and rerun benchmarks in math, code, STEM reasoning, and instruction following. We compare the base model, an intermediate checkpoint, and the final model after extended training. Our key finding is that the initial capabilities of the base model significantly influence how much ProRL can enhance reasoning. We notice a strong negative correlation between the base model's reasoning ability and the improvements seen after RL training. Specifically, tasks where the base model performs well show little to no gains in reasoning breadth after RL, indicating that the model becomes more confident in familiar solutions rather than exploring new reasoning patterns. Conversely, in areas where the base model struggles, particularly with low initial performance, ProRL is most effective, improving not only the model's accuracy but also its ability to tackle a wider range of reasoning tasks. To further validate our observation that tasks with minimal gains post-RL are those the base model already knows, we calculate a creativity index for the base model's responses. This index measures how much the model's answers overlap with a large pre-training dataset. We find that tasks with lower creativity indices, particularly in math and code, suggest the base model has encountered similar data during pre-training. We analyze performance trends on individual benchmarks and categorize them based on how performance evolves during training. Our findings show that reinforcement learning can significantly enhance a model's reasoning capacity, especially on challenging tasks. While some tasks reach a plateau or even regress, we also see clear examples where reasoning capabilities improve with continued training. Notably, in areas like code generation, ProRL allows for ongoing gains, indicating that extended training helps the model learn more complex reasoning patterns. In some benchmarks, particularly in math, we observe that the final model shows decreased or unchanged reasoning capacity compared to the base model. Although accuracy improves, broader reasoning ability often declines, suggesting that the base model already had sufficient reasoning skills, and RL training mainly fine-tunes outputs without encouraging exploration. For other tasks, RL training boosts both accuracy and broader reasoning ability, but these improvements are mostly achieved early on. Comparing intermediate and final checkpoints reveals that ProRL provides little additional benefit, indicating that the model quickly reaches its learning potential for these tasks. In contrast, for more complex benchmarks like coding, we see continued improvements in reasoning capacity with extended RL training. These tasks likely require extensive exploration during training to generalize well to new problems, allowing ProRL to expand the model's reasoning boundaries. We also examine how ProRL affects the model's ability to generalize beyond its training data. We focus on tasks that were not encountered during initial training. For instance, when we evaluate the model on a task from the reasoning gym that it has never seen, the base model fails to solve it, while the ProRL trained model shows significant capability, indicating an expansion in reasoning boundaries. Furthermore, when comparing an intermediate RL checkpoint with the final model, we find that extended training consistently enhances performance across various tasks. This supports our conclusion that ProRL helps the model internalize abstract reasoning patterns that generalize beyond specific training scenarios. Lastly, we assess performance across different levels of task difficulty using a graph coloring task. Although the training data only includes smaller graphs, we test on larger ones to evaluate generalization. We observe a decline in performance as task difficulty increases, which is expected due to the growing complexity of solutions. However, our ProRL model maintains significantly higher accuracy across all graph sizes compared to both the base and intermediate models, demonstrating that extended RL updates improve not only in distribution tasks but also the model's robustness to more complex, unseen challenges. Section Summary. In this section, we evaluate the impact of prolonged ProRL training on reasoning capabilities by analyzing performance across various tasks. Our findings indicate that while ProRL enhances reasoning for models starting with lower initial capabilities, it can lead to diminished or plateaued gains for those already performing well, suggesting that extended training is most beneficial for challenging tasks and out-of-distribution scenarios. Section: How does pass-at-1 distributions evolve as ProRL progresses? In this section, we explore how the pass-at-1 distributions change as our ProRL method progresses. Dang et al. Established a mathematical upper limit for pass-at-k, where pass-at-1 accuracy for a specific task is represented by ρ_x. We found that while increasing expected pass-at-1 raises this limit, higher variance can lower it. Contrary to previous observations of decreasing pass-at-k during training, our results show continuous improvement in both pass-at-1 and pass-at-1/6, aligning with the scaling law patterns seen in OpenAI's o1RL training. Our ProRL approach leads to significant performance enhancements across various tasks. Figures A and B reveal notable shifts in the distribution for code and logic puzzle tasks. Initially, the pass-at-1 distributions were mostly near zero with long tails, but they changed significantly after training. For example, Codeforce's problems showed a wider distribution after training, while the family_relationships task, a new reasoning challenge, shifted dramatically from mostly zero accuracy to achieving perfect accuracy, indicating successful problem solving across most prompts. These substantial distribution changes, resulting from extended RL training, improve expected pass-at-1 enough to counteract any negative impacts from increased variance. In the related work section, we discuss reasoning models, which are specialized AI systems that perform detailed reasoning before arriving at answers, a concept introduced by OpenAI's o1 models. Following this, DeepSeek and Kimi outlined methods for training reasoning models using reinforcement learning with verifiable rewards. These approaches have popularized various RL algorithms. While many open-source projects have tried to replicate o1-like models, most focus on single domains or test-time compute scaling, with few addressing long-term reinforcement learning training or its scaling laws. We acknowledge that RL training is challenging due to its sensitivity to hyperparameters, and various techniques have been explored to improve training stability. Our research shows that prolonged RL training can significantly enhance the reasoning capabilities of these models. Achieving superhuman performance has been a key goal in machine learning, with reinforcement learning algorithms, starting from deep Q networks for Atari games, showing promise. Recent examples like AlphaGo and AlphaZero illustrate that AI agents can continuously improve their performance through iterative data collection and policy enhancement. However, some recent studies challenge the idea that RL training truly enhances the reasoning abilities of large language models. One study suggests that the RLVR method does not extend reasoning capacity, as indicated by pass-at-k metrics showing no improvement or even decline compared to base models. Another study found that RL algorithms often converge to a dominant output distribution, merely amplifying existing patterns. We also consider alternative measures, like the creativity index, to assess whether models learn new ideas through RL training, which we incorporate in our studies.